ahead that they're working on the 5th assignment. I know probably a lot of you aren't even near that, but there's going to be a couple of additional hints added to that and rephrasings and rewordings of it that might make it easier. So try downloading it from the web again in a couple of days after I make those changes. It might be a little easier. Okay, so this is now the 15th lecture for the condensed matter course. We're coming to the stunning conclusion at some point. Where we left off, we were thinking about the nearly free electron model. Nearly free electrons. And just to remind you how this worked, and I know I went through it rather rapidly at the end of the last lecture, so I'm going to go through it again. We start with a parabolic spectrum of free electrons, K naught, and we add a periodic potential. And at K, so K is in this direction, at K equals pi over A minus pi over A, minus pi over A here, you have two states of the same energy which differ from each other by a reciprocal lattice vector. And as a result, in second order perturbation theory, we have a divergence, so we have to handle this situation with degenerate perturbation theory. And the rules of degenerate perturbation theory is you should take the two offending states, the two states with the same energy that are causing the divergence, and you should diagonalize the Hamiltonian within that space separately. So we took K and K plus G. In this case, well, there it's minus pi over A. And we wrote a 2 by 2 Hamiltonian to describe those two states. And the Hamiltonian looked like V sub K naught plus V0, V sub G star, V sub G, V sub K plus G0 plus V naught. And then we have to diagonalize this Hamiltonian to find out what happens to our two degenerate states. Now, a couple of comments. First of all, for homework, you're going to consider the case where K is not quite on a Brown zone boundary. So, for example, you might take this point here and this point here, which are separated by a reciprocal lattice vector. So they're not quite degenerate. So V sub K and V sub K plus G don't have to be quite the same. It's a little algebraically more difficult, but it's spiritually the same thing. But here we're going to make our life easier by assuming E sub K equals E sub K plus G. In other words, assume K is at BZ boundary. In this case, the Hamiltonian we're diagonalizing is very simple. It has two identical elements on the diagonal, and then it has off-diagonal elements that are complex conjugates of each other. So you get two eigenstates, E plus or minus is E sub K naught plus V0 plus or minus absolute VG. Now something, I'm not very clear about this in the notes, and I wasn't clear about this yesterday, but this overall shift in energy V naught is uninteresting. So I'm just going to ignore it. Ignore. So having ignored that piece, our new, sorry, just hold that on the bottom, I'll roll it back up in a second. Our new spectrum opens up a gap at the Brown zone boundary. This, and like this, like this, and like this. So that to accommodate the fact that the energies have been shifted up and down by VG. And since I'm not very good with drawing these things and making them clear, I'll show you a real picture of it. So here it is in the extended zone scheme. You start with this nice parabola, and then at the Brown zone boundary, these two states are connected together by a reciprocal lattice vector, so they can scatter into each other and open up this gap at the Brown zone boundary. The closer you are to the boundary, the more effective this scattering is, and the more you deviate from the original parabola. Now, of course, Bloch's theorem tells us that we're allowed to plot everything in the within the first Brown zone. So I can move this piece of the dispersion curve to over here, this piece of the dispersion curve to over here, and we get a nice reduced zone scheme plot of the excitation spectrum, with the gap being 2 times V sub G, that being the V sub G, to remind you, is the Fourier component, Fourier transform of periodic potential at wave vector g. Okay. Now, in order to develop a little bit more intuition for what this means, we're going to do an example, simple example, where we have a very simple periodic potential. V of x is 2 v tilde cosine 2 pi over a times x. So the Fourier components of this potential are just v sub g equals v twiddle for g equals plus or minus 2 pi over a and equals 0 otherwise. So that potential has a Fourier component that connects together minus pi over a and pi over a only. So let's see if we can figure out why it is that this gap is opening up. What's causing this gap in this model potential? Actually, maybe I'll use this one now. So just to plot the potential, it's a nice cosine potential, like this. So this point here is a, this is 0, this is minus a over here. Nice periodic cosine potential. And we know that what we're mixing together with this potential is we're mixing k equals minus pi over a with k equals pi over a. These two kets. And if you write them in real space, that's e to the I pi over ax and e to the minus I pi over ax are the two wave functions that get mixed together by this periodic potential. Now, the Hamiltonian that one diagonalizes is 2 by 2 Hamiltonian. If you're on the de Broglie zone boundary, it's extremely simple. 2 identical terms along the diagonal and then an off-diagonal term here. So the two eigenstates can be simply calculated. I won't do that for you, but you can trust me on this. The positive energy eigenstate, the psi plus, the higher energy eigenstate corresponding to E plus, is then the symmetric combination of these two, over ax, whereas the lower energy eigenstate is the antisymmetric combination of these two. Maybe I shouldn't call it. Well, okay. Hasn't been this time. This. And then we can look at the corresponding probability amplitudes of these two wave functions. So psi plus squared is proportional to cosine squared of pi over ax. And psi minus squared is proportional to sine squared of pi over ax. And so if we plot those over here, so this is sine squared of pi over ax, this one. So sine squared is sine minus squared, so there's a sine minus squared here. And then another color, we have psi plus squared. Okay? So what you see is we've combined together these two plane waves, the k equals pi over a plane wave and the k equals minus pi over a plane wave, to make these two cosine-like wave functions. And one of the cosine-like wave functions, the psi plus, is sort of located near where the potential, this white curve is v of x, where the potential is mostly positive. So psi plus, psi plus has its amplitude where the potential is mostly above 0, like here and here, whereas psi minus has its amplitude where the potential is mostly negative, like down here. So psi plus is mainly sees v plus, whereas psi minus mainly sees v minus. And that is more or less why it is that these two states get pushed up and down in energy respectively. The combination of these two plane waves that combine together to make two combinations, one which gets a maximum amount of energy by putting in most of its amplitude on the plus part of the potential, one of them which gets a minimum energy by putting most of its amplitude on the negative part of the potential. And that sort of gives us some intuition for why it is that these two states split from each other and one goes up and one goes down. Okay? Good? Happy? All right. Now the story is not too much more complicated in 2 and 3 dimensions. So let's consider a 2-dimensional case, 2D square lattice. This. And I'm going to plot the reciprocal lattice, which is also square. Not this square. Square. So let me see if I can do that. Okay, draw a square lattice. This. Okay, the point in the center is the reciprocal lattice point 0. And before we add the periodic potential, in this nearly free electron picture, before we add this periodic potential, we have a nice parabolic dispersion. The free electron parabolic dispersion, h bar squared k squared over 2m, centered around this g equals 0 point. Now, once we add the periodic potential, we should open up gaps at the Broughton-Zone boundary. And we actually looked at this case, where's the Broughton-Zone boundary? It forms a nice square around g equals 0. So this is the BZ boundary. Here. And gaps will open up at the Broughton-Zone boundary because for any point you choose on the Broughton-Zone boundary, like here, there will be another point separated from it by some reciprocal lattice vector g over here. So the wave, the k state here and the k state here will mix into each other because of the periodic potential, because of the Fourier component of the potential at that wave vector. They'll mix with each other and they'll open up a gap exactly the same way as it did in 1 dimension. And the general principle will be that states inside BZ1 get pushed down, whereas states outside pushed up. And you can see that in this 1-dimensional picture in the extended zone scheme, with the states close to the Broughton-Zone boundary, but inside the first Broughton-Zone have been pushed down from their free value, whereas the state outside the Broughton-Zone boundary get pushed up from their free electron value. Now, there is one little complication when you're in 2 dimensions or 3 dimensions that doesn't happen in 1 dimension, and that is when you happen to be at special points like these corner points. So corner points here have the interesting property. Let's just label these. 1, 2, 3, 4. So they're all the same if this is square. They should all be the same distance from g equals 0. So they all have the same energy before we add the periodic potential. But they're all also separated from each other by reciprocal lattice vectors. These are all reciprocal lattice vectors. Actually, all of these are reciprocal lattice vectors. And so, in fact, all 4 states mix into each other instead of just 2 states mixing into each other. So, in this case, we would write a trial wave function which would be of the form phi 1